Okay, looking at calculus day 1 of Unit 1, I'm going to totally insult your intelligence, although I'm not meaning to. Because we need to create equations of secant lines and tangent lines, we're just going to quickly review things that we did in grade 9 and 10, making sure that we can determine the equation of a line. So if you have a slope of 2/3 and a y-intercept of 4, the equation of a line that we like the best is y equals mx plus b form, slope y-intercept form. So we would have y equals 2/3 x plus 4. Don't forget this stuff when we get to tangent lines. B. If we want the equation of a line that passes through 2 points, we need to determine the bits and pieces from y equals mx plus b. We need the slope and the y-intercept. So from grade 9, we did the slope over and over again is rise over run. So that rate of change. For this one, we are looking at 2 points. So we are going to look at delta y over delta x, or y2 minus y1 over x2 subtract x1. So in the order point A and B, we have our rise as 8 subtract 4, and our run as -6 subtract -2, for a slope of 4 over -4, which is -1. In order to determine that y-intercept, we need to substitute a point. So we're going to choose a point. Either or is fine. I like -2, 4 best. And I do talk fast, but not usually this fast. Substitute that point into y equals -1x plus b, just to show what I'm doing. Subsequent line would be 4 equals -1 times -2 plus b. I want to solve for b by subtracting 2 from both sides. B is 2. Final answer, y equals -1x plus 2. So those two questions in a minute and a quarter was all of grade 9. C. We are looking to find the equation of a line where I have given you the slope and passes through a point. I gotta call it J because that's such a cool letter. 1, 3. Same process of thinking. I want y equals mx plus b. Since I have the slope of -3, I'm going to substitute that point into y equals -3x plus b to solve for the y-intercept and have the equation of my line. 3 equals -3 times the x value plus b. I'm going to add 3 to both sides to have, oh, I shouldn't do b's and 6's, sorry. Y equals -3x plus 6, final answer. The next question that we're going to look at is a little bit of review from grade 11, function understanding, and grade 12, piecewise. We don't really look at piecewise in grade 11, but those two things put together, we have this function f of x, and it's root of 3 minus x for x less than 0, and 3 plus x if x is greater than or equal to 0, and we want to compute each of the following values. So the new thinking was function notation and piecewise, and we're going to compute f at -33. And in that particular case, I'm at the top half of that listed function, so I have 3 subtract -33, which is the square root of 36, which coincidentally is a nice number, but that function has that value at that point. F at 0 comes from the x greater than or equal to 0 section of that piecewise function, and we have 3 plus the value of x, so we're looking for the square root of 3. Lastly, f at 78. Same idea, it's in the second half of that piecewise function. I shouldn't say half, it's bad for 3 plus 78, which is the root of 81, which is 9. Also coming from grade 11 was that transformational understanding, which is so key for graphing. Let's go with red for danger. Transformations was the big idea in grade 11. Okay. So for this particular function, my parent function is y equals root x. My transformations are simple. They're simply inside the function, a change of 3 in both cases. So if you are changing something inside with the x value, that is going to be a horizontal change. If we had a plus 3 or a subtract 3 out the end, that would have been a vertical change. Okay, inside the function, horizontal change, since it's an addition of some sort, we're going to have a left or a shift, shift or translation, whichever word you like better. Since it's a horizontal shift or translation, it's going to be a left-right change. Lastly, before we graph it, lastly, I see inside here, inside the function with x, so as a horizontal change, I see a negative. Horizontal. Multiplying by a negative is a flip or reflection. So we're going to have a horizontal reflection as well. Okay, I'm making a bit of a mess here, so before I draw it, I'm just going to draw this thing down here. If f at x equals square root of 3 subtract x for x less than 0, I'm going to just rewrite that piece, red for danger, as negative x subtract 3. That's the same thing as what's directly above it. That's a little bit easier to see. So this function is a horizontal reflection. It's going to the left instead of to the right. It has also been shifted 3 to the right. So 3 to the right and reflected. So my parent function was the square root of x function, which looks like this. Sorry, can't do two things at once very well. There is my parent function. Reflected and 3 to the right would look like this. Ooh, not too bad for an old lady. Okay, so those are my reflections, but that only applies for x less than 0. So I'm going to erase the part that's greater than or equal to 0. Wah, wah, wah. There we go. Okay. The other part of that piecewise function is the square root of 3 plus x when x is greater than or equal to 0. That is the square root function as well, and that is 3 to the left. Things are backwards when they're horizontal shifts. So I've got this function, 4, 2, there we go. So that would be the square root function, move 3 to the left, but it is only in the interval x greater than or equal to 0. So I'm going to erase that piece. And it is a continuous function because it hits the same value when x equals 0 from both directions. We're going to talk about that a little bit more. And we have graphed that from our understanding of transformations from grade 11. Our next review problem is definitely your favorite, rationalizing the denominators. We looked at that in grade 11 for sure, and you looked at rational functions and so on in grade 12 a little bit too. So if we're going to rationalize the denominator, we want to be able to have a, quote, nice denominator, unquote, so that we can add and subtract these rational expressions without a great deal of pain. So we just don't like the root sign on the bottom. So in order to get rid of root 3, we can multiply by 1, which is root 3 over root 3 which can get rid of the radical on the bottom, but we don't care about the numerator so much. I would be left with 5 root 3, ugly as it is acceptable, over 2 times regular 3, or root of 9. 5 root 3 over 6, best answer. The second one is a little bit trickier. 3 root 2 over 2 root 3 subtract 5. We've got a bit of a mess on the bottom there. I want to rationalize that denominator. I want to get rid of the root 3 part. So my thinking is an undoing of a difference of squares. So if I have 2 root 3 plus 5, I'm going to have firsts. We'll square that root 3 and get rid of the outside-inside term by having opposite sign. So I'm going to multiply by 1, 2 root 3 plus 5 over 2 root 3 plus 5. I will end up with 3 root 2 times 2 root 3 plus 5. We can tidy that up if we want to. The bottom, I am multiplying to what look like binomials. So my thinking is I am foiling, and I am foiling a difference of squares. So my firsts would be 4 root 9, or 4 times 3. Outside would be 10 root 3. Inside would be subtract 10 root 3, subtract 25. So let's just do this thing. I have 6 root 6 plus 15 root 2, and I'm not sure that's any nicer, over 12, gone, subtract 25. 6 root 6 plus 15 root 2 over negative 13. We call that the conjugate, which is the opposite or opposite sign. If you want to impress people, you're multiplying by the conjugate. Thinking from grade 11 and grade 12 for sure, we introduced the thoughts of domain and range, domain in particular, in grade 11. And then you have to use that for asymptote understanding last year. So I'm asking you for what is the domain of each of the following. Good thought process would be, by the way, what does this thing look like? I know that the parent function is the root of x. And the parent function has the domain that x is greater than or equal to 0. So that's my thinking. I am taking that basic function and I am doing what with it? I have a horizontal change inside the brackets, or sorry, inside the invisible implied brackets, inside the function. And it is always opposite to what you might expect when it's a horizontal change, but it's going to be horizontal left 4. So my domain gets changed. We have moved it left 4. So my domain is going to be x is a real number, x greater than or equal to negative 4. Okay. The second one, I have 4 over 7 subtract x. I'm just pausing here because I'm trying to figure out where to draw it. Okay. The reciprocal function, and I have a problem when x is 7. So I have a vertical asymptote because x cannot be 7. And I know that I have a function that approaches that value and approaches a horizontal asymptote as well, since the degree on the bottom is 1 higher than the top. So we're going to have a function that looks like that. It can just help your brain to get into gear to come up with a diagram. Okay. So the domain for my regular reciprocal function would be x cannot be 0, but this one, x cannot be 7. So my domain would be x is a real number, except that x cannot be 7. the last one. Let's rewrite that one. Our denominator cannot be 0. So we know for this last one, we're going to have problems when x is 1 or negative 1. If you can picture this thing, it is going to have vertical asymptotes at 1 and at negative 1. It is going to approach a horizontal asymptote on both sides. And, oh wow, bad. But anyways, our domain would be, thinking about asymptotes, x is a real number, however, x cannot be 1 or negative 1. Sneak an x in there. Fantastic. I'm going to walk through 2 examples of rate of change. We may or may not get them today. You finish them today. You may want to look at that tonight and be ready for tomorrow. We're going to do an investigation tomorrow, so there's no video for that anyways. But our rate of change for this thing, it's a Bunsen burner and we're heating water in a beaker. And we're showing how the temperature goes up every 5 seconds, and we have a graph. We are asking you to calculate the average rate of change over the following intervals. So from 0 to 80 seconds, so I'm looking at the whole shebang, what is that average rate of change? So to draw it as a diagram, I am looking for that secant between the first point and the last point. I'm looking for the rate of change from beginning to the end. Just like to change the color so we can see it. Okay. So from 0 to 80 seconds, I am changing 80 degrees. 80 degrees in 80 seconds. So my rate of change is 1 degree per second. But that really doesn't seem reflective to me, looking at that diagram, about what is happening, not representing that story very well at all. If we narrow our interval a little bit, if we go from 0 to 30, there we go, we are looking for the secant from that first point to 30. Let's see if I can hone in on that. Right, perhaps a little more reflective of the first part, but certainly not a good representation of the second part. But our rate of change would be, we are going from 0, so from 20 to 80. So we have gone, we've had a change of 60 degrees in 30 seconds. So we have changed 2 degrees per second, which is a much faster rate of change, but not necessarily representative of what's going on. The second section seems to have chilled a little bit, from 50 to 80. Okay, these are old eyes trying to see this. Narrower interval seems to look a little more appropriate for that part of the data. So our change would be, we ended at 100 degrees from 91.4, so my delta y, in 30 seconds, which is approximately 0.29 degrees per second. Okay, so something you know already is that the average rate of change of y with respect to x is our delta y over delta x. Now we want to look at the instantaneous rate of change when t is 35. So looking back, I want to know, let's go pink, when t is 35 is right there, and I'm trying to eyeball this. I am looking for the instantaneous rate of change, what's happening right at t equals 35. So we are looking at decreasing intervals to see if we can come up with the best approximation. So let's look first of all from the interval from 20 to 50 seconds and see what the rate of change is. From 20 to 50, I have delta y over delta x, which is 91.4 subtract 70 over 30. I don't like this, doing these videos, not having you guys talk to me. Okay, I am getting 0.713 approximately degrees per second as my rate of change over that interval. If I narrow that interval a little bit, I go from 30 to 40. My delta y over delta x would be 86.7 to 80 in 10 seconds. It's approximately 0.67 degrees per second. If we had more data, we could continue narrowing our interval and see what that value approaches. It appears to be getting closer to 0.69 degrees per second, something like that. And so the big idea is that the instantaneous rate of change of y with respect to x at x1 is the slope of the tangent that touches our curve at only one spot to the graph of the function at the point where x equals x1. Okay, last example is about antiseptic spray. It's sprayed to a culture of bacteria and things are dying. So we have exponential decay, which is what we would expect. So we have the secant, which is hard for you to see perhaps. And it's looking at that average rate of change when from time 5 to time 35. And we're going to calculate that in a second, talk about what it means. And then we want to look at the instantaneous rate of change, where our graph didn't photocopy very well, so you're going to trust me on a point, which is a dangerous proposition. Okay, so if we're looking for that secant slope from time 5 to time 35, I am looking for delta y over delta x. So my secant slope would be from 80 down to 26 in 5 to 35 minutes. So we are doing percent per minute, which is 54 over negative 30, which is negative 1.8% per minute. That's our secant slope. The instantaneous rate of change, we know we want it at t equals 20. I know I have the point 2043 because I'm blindly trusting my graph. And I want to determine the equation of that instantaneous rate of change, that tangent line. I am going to have to go by another point on the graph. I don't have any further tools at this point. Are you catching my hint there? So if you trust me, there is a point that is quite clear on my graph. That's 4010. So we are trusting our eyeballs, which is very dangerous. Those are supposed to be eyeballs, which is very dangerous. But we want to determine the equation of the tangent, which we believe passes through 4010. So the slope of our tangent line is 43 subtract 10 over 20 subtract 40. So our delta y over delta x becomes our slope 33 over negative 20, which is negative 1.65, which is our instantaneous rate of change at the tangent line. Let's continue and create the equation. So if I want the equation of the tangent line, I want to substitute a point into y equals negative 1.65x plus b. 10. And again, you're blindly trusting my arithmetic, so if you have a calculator handy, you should always check. Negative 66 plus b, add 66 to both sides. Final answer. The equation of my tangent line is y equals negative 1.65x plus 76. Does that look representative on the graph? Where is it? 76, sure. Looks pretty reasonable. You have some assigned questions online and a Frayer model to fill out for AROC and IROC. There are ideas pinned up to the front board, and I have solutions for all your homework questions as well pinned to the front board.